His topic is equivariant Weierstrass theory.
Thank you very much, David. I'm very thankful to organizers for making this possibility to gather here, organize this beautiful conference, and certainly it's a pity, big pity that Alex cannot join us right now. But, probably here I know Alex older than from more time than anyone else. So we met for the first time. I think it was December 78, and you were still 4-year students. That was 5th year student. December 78, and for me it was a, so to say, black day of my life. I can tell you why, because I was a 5th year student. I was working on my master thesis, and we had last semester, we didn't have classes. We don't have to do anything, just write work on master thesis. Those who wanted to get written work, and also we need to prepare to some exam, which was on the subject, which was called, absolutely seriously, scientific communism. Yeah, today it sounds like a joke, but there was a huge exam. You need to learn by heart a lot of things, and it was called scientific communism. So, and somehow in November, my advisor, Anatoly Grishin, he gave me a question. It was, well, it was mentioned probably in some papers that this is an open question, whether there exist entire functions of growth as close as possible to log square R with some field property. And in November, I think I did this, and then I thought that I have free half a year. I will go to Crimea to do some hiking, to drink good wine, I don't know, to enjoy life. And then Alex, he was still in Lviv that time, came to give a talk at complex analysis seminar, and that was his joint work with his advisor, with Anatoly Goldberg, and they did what I did, but much more. They constructed functions even with much more properties, and properties which were in my functions were just a special case. Their function was much more weird than mine. And for me, this was a disaster, because all my plans were ruined. I asked for another question, my advisor for another question. It was also some question, open question from some book, and I worked very hard for it. I did it, but this was really a black day of my life. And then after Alex moved to Kharkiv, it was maybe half a year after this, slightly more. We very fast started to be very close friends. We started to work together for 8 or 9 years. We worked very intensively. He's still I wrote with Alex more papers which I wrote with anyone else. It's not vice versa. With Walter and Andrei, Alex collaborated more after he moved to the West. But we talked a lot. I learned a lot of things from him. We met twice a week to discuss mathematics, and we had even some programs what to do, and partially fulfilled. And I learned a lot from Alex, and thank you for all this. And what I wanted to tell you today is my joint work, which is still in progress, with Konstantin Slutsky. He's from Iowa State University, and Aaron Wenman. And we started, Aaron was postdoc at Tel Aviv, but now he has a position at Leuven. And it's also related to Alex. So at least not the origin of this particular question, but all this, my interest to this direction. I think it was in January or February 98 in Tel Aviv. We were sitting with Alex on a lecture of Gromov, and Gromov in his lecture, this was basically about mean dimension, what we heard from Masaki 2 days ago. But Gromov said that there is a direction in the theory of entire meromorphic functions, which from his point of view, experts in Nivadlina theory completely missed. And this was more or less exactly his words. And somehow with Alex, we jumped. But then there was a ramification. Gromov mentioned both. He mentioned both questions related to study of Brody curves and mean dimension, but also a paper with which Benji Weiss, which is also related to action of complex plane by translations, wrote recently, and he said also explicitly that he thinks it would be very good to understand what is written there. And somehow after this, we diverged, so Alex started to think and to be interested in Brody curves, and they just reflected our interest. We didn't do this on purpose, and I tried to understand what is written in this paper of Benji Weiss, which was not a simple thing. So I asked several colleagues of mine to look at it, and somehow it's 7 pages paper. First 3 pages are completely clear, but last pages are references and open questions, and 3 pages in between, for me, were completely incomprehensible. Then I had the luck, I had Adi, who is sitting here as a PhD student, so and Adi had a background in ergodic theory and in abstract thinking, but also for Adi it took maybe 1.5 years to understand. We discuss this quite often, and it took 1.5 years to understand these 3 pages. They're not related directly to what I plan to talk to you today, but in the end, I will make connection. If to speak, it is more or less the same direction. It still will be action of complex plane by translations on entire functions. But this is what we heard from Masaki, but there are 2 extreme cases. In Masaki case, there was a compact subspace of meromorphic functions or meromorphic entire curves, which are called Brody curves. So action was on a compact set. In my case, action will be on the set, which is very far from being compact. Okay, so this was an introduction, and now let me move to mathematics. So we have a space of entire functions. With locally uniform topology. We have a space, I call them configurations. It's a discrete multiset. It's a divide. Both are, here we also can introduce a weak topology, and both are complete metric or we have a each entire function, we have it 0. 0. So this is a continuous map. We teach students, so if sequences of entire functions converge, then zeros also weakly converge. And the Weierstrass theorem, which we teach undergraduate students, says that there exists a right inverse.
I guess your functions are non-constant.
Yes. So there exists right inverse. So this map is surjective. But now, saying this, we forget about additional very important feature. That complex plane acts both on E and on configurations by translations. EZ TW F Z plus W if we want to balance, and E, I will denote the same E W F on some configuration. To shift argument is the same as to shift zeros. And then a very natural question is whether there exists an equivariant inverse. That is a map from configurations to entire functions, which would commute with action of the complex plane. Certainly, first of all, there is a simple obstacle. Let's remove it. Liouville theory. If our configuration was doubly periodic, then if our map is equivariant, entire function has to be doubly periodic, and this cannot happen. So if we remove for time being only also one periodic configurations, I will speak about one periodic case a little bit later. So let me assume that C acts on configurations freely, that we don't have periodic points. So this means that I remove from consideration periodic configurations. I want to build equivariant inverse on non-periodic configuration. Certainly, if you don't care about properties of this map, and if you allow yourself to use axiom of choice, it's a simple exercise. Because the action is free, so we have, so this space is a set of orbits. Each orbit is like complex plane. So by axiom of choice, we pick up one point from each orbit, one particular configuration. We apply Weierstrass, classical Weierstrass theorem, and then we shift in the opposite. Then if we take another point in the configuration, there is well-defined translations because of freeness of the action. So we simply shift what we got in the opposite direction. So if you don't care about properties of this map, you use axiom of choice, and such map exists. So set theoretic construction is a simple exercise. On the other hand, it's not difficult to see that there is no continuous. It's also not so difficult to guess why. The reason is very simple. In the space of our configurations, there are plenty of compact invariant subsets. For instance, you can use almost periodic, you can construct almost periodic sets which are compact invariant or minimal. So it's very easy to construct compact invariant subsets of these divisors, of these configurations. If our map would be continuous, it would map this compact invariant space of divisors, set of divisors, into compact invariant sets of entire functions. But on entire functions, by the same Liouville theorem, there are no compact invariant subsets, because if it is compact, then say point evaluation at the origin would be bounded uniformly. It's continuous functional. It would be bounded on the whole set. And because of it is invariant, all functions would be bounded. So only constants are in compact invariant sets. So there is no continuous map. So the only possibility which remains to us is to work in measurable category. So what about at least I don't see any other choice how to what to do in this situation. So our main theorem says that there exists right variant inverse. You can indeed construct a version of Weierstrass theorem which would give you equivariant map, which would commute with translations. I should tell you that functions from the set, this will by far classical canonical products cannot give you this. Because in canonical products, in all constructions which use canonical product, we fix one point in the complex plane. These functions, even if you will start with configurations which are have number of points in disk of radius r grows like r square, all these functions by result which we had with Lev Bukovsky ID and Sasha Logunov earlier will have infinite order of growth. These are exotic, in that sense, these are exotic or esoteric functions. Maybe a few words. So certainly there is a meromorphic, because today we speak formally about meromorphic. Today is a meromorphic function day. So there is a meromorphic version of this theorem. For meromorphic version of this, there is a meromorphic version of this theorem, but there is one difference with, it's not immediate corollary of this formulation. And I can explain you why. Because in usual Weierstrass theorem, if we prove Weierstrass theorem and we have divisors of poles for zeros and poles, we can construct two and divide. But here, for instance, divisor of zeros and poles would be free, action would be free, but zeros are doubly periodic with one period, poles are doubly periodic with an immeasurable period. So action is free, but you cannot get entire function separately for zeros and poles. That's why you need to be more careful in this construction. Now, maybe I will tell you a few words about. Can I erase this? One periodic case. One periodic case is cylinders, right? It's a little bit unexpected, at least for us, that there is no barrel equivariant from. When I write one periodic, I mean that they have one period, but you may think that the period is one. The reason for this, there is a nice exercise which I will only give a hint, and I think many people here can do themselves very fast. That if P is a probability measure, on one periodic entire functions, with respect to translations, I don't need even all translations. Enough to consider only integer translations along imaginary vectors. So E1 is equal to 1. Then it is trivial. It is supported by constants. So this says that there is no non-trivial invariant probability measures on cylinders, non-trivial around with respect to translations in the direction of the cylinder. And if there would exist such a map, certainly there are plenty of such measures and configurations. If there would exist such a map, you will come to contradiction. Why this is so? The reason is Birkhoff-ergodic theorem. So if such measure, if P is such a measure, then by Birkhoff-ergodic theorem, this is really an exercise for almost every P, almost every function f, which is one periodic, there exists a random constant, positive could be large, and random integer sequences Sn and Pn, which tends to plus infinity, such that absolute value of f is less or equal than m on these two segments. We make a here. Minus I Sn. What I'm saying that every function from support of our measure has to be bounded on this segment and on this segment. And because our functions are one periodic, they will be bounded on the boundary of the strip, and by simplest fragment Lindelöf, they will be bounded everywhere in the complex plane, so they will be constant functions. So this is a hint, but this was quite unexpected, why there are no non-trivial measures on one invariant entire functions. On one invariant meromorphic functions, there are plenty of very interesting non-trivial measures which are related to this Yesida class of normal meromorphic functions. Maybe now, before I will start to discuss the proof, I will say a few words about the proof. I will tell you a few words why we started to be interested in this. So our original motivation came from this, that suppose that lambda, let's forget about multiplicities. It's suppose that lambda is a simple point process. Simple point process means that probability measures on discrete configurations, but I don't care. All multiplicities are one. And I'm interested in probability measure. Non-periodic. So then, let me denote this by W capital Weierstrass inverse. So if you use Weierstrass theorem, you can lift this configuration to space of entire functions. There exists entire function with these zeros. But if this configuration was stationary, so distribution of lambda is stationary, which means that it has translation invariant distribution. We want to lift it on a space of entire functions, again, making it stationary. We want to build entire function which has the zeros, but also when we shift configuration, we shift entire function, and we want to have distribution of this entire function the same as it was before the shift, before the transition. And originally with my PhD student, Warren Yakir, here, and Aaron, we did this. So for some reason we were lazy to, not lazy, but so we didn't make it public. But if you have any stationary point process in the complex plane, which is non-periodic, then you can lift it to stationary entire function. So we can build, so there exists random entire function. zero set lambda and this translation and meaning. But our procedure did this for every process. We had to build this function anew, and that's why we were interested. I became interested in the question that maybe there is one map which can do the lifts for any random processes, point processes. I don't care whether they're stationary, non-stationary. There is a small issue here of how to understand measurability in Borel sense or in Lebesgue sense, but let's put it aside. It's really a technical issue. And our theorem says that you don't need to prove this theorem each time for each point process. In you, there is one map which can do this all point processes. Another remark is, this is what I already mentioned briefly, why Hadamard construction doesn't work. Even for this lift. Why? Because if you will try to do, so let's start with process, I don't know, with very simple processes like Poisson point process, when you have distribution of zeros in disjoint domains, in disjoint domain sets are independent, and number of zeros is mean number of zeros is proportional to the area of the set. So you can build, of course, you can build a canonical product. You can even regularize it. You need to understand it in principal value sense at infinity to write product of absolute value of lambda is less than r, then send r to infinity, everything will be convergent. But what will happen if you will start to shift lambda? If you will start to shift lambda, this function will be multiplied by e to the random linear function. And this random linear function will be a kind of cocycle. It doesn't change zeros, it doesn't change zero set, but the distribution of shifted function will not be the same as distribution of the original function. That's why this construction doesn't. And another remark is that by the result which I mentioned already, these functions with Bukovsky, Adi, and Sasha Logunov, the function which we constructed, they're pretty wild. First of all, they grow, they have infinite order of growth. Even if this divisor was okay. But also they had very heavy tails. If you look at their moments, they don't have expectation. They don't have logarithmic expectation. The best you can hope for is a second logarithmic moment. That only expectation of log of absolute value of f at some point up to some epsilons can be finite. So these functions are really wild, have a wild behavior. And now I will tell you a few words about the proof. Actually, there are two proofs of, at least I know at least two proofs of Weierstrass theorem. One proof which we usually give in complex analysis courses built on construction of Weierstrass infinite product, but there is another proof which probably people in several complex variable appreciate more, which is based on Runge's theorem. So the first ingredient of the proof also in our situation is Runge approximation. We need it in the simplest version that if you have a compact, if K is a compact set and complement to this set is connected, then for any analytic function H, okay, which means it's some neighborhood of K, and for any epsilon, there exists a polynomial P such that norm of F minus P here, P is less than. So you can glue different pieces. You can patch different pieces in one function.
So it's H, not F.
H, thank you, Lesson. Yeah, it's really great theory. One of probably greatest theory in complex analysis. But when you prove Weierstrass theorem using Runge's theorem, classical Weierstrass theorem, what do you do? You start with exhaustion of complex plane by bigger and bigger sets, and then you first make polynomial, take part of divisor in a smaller set, take polynomials. This is the first step of induction. Take a polynomial with the zeros, and then you consider a bigger set. You want to add zeros on a bigger set again in the form of polynomial, but then because you have a freedom in exponential factor, using Runge's theorem, you correct your right factor e to the power phi to make new guy close to what you had before on the previous set, etc. And you expand, and you got. Why? Where we have a trouble here, we need to do this in equivariant and in Borel way. So if we start to do this in different orbits, no one will tell us that we will get a Borel construction. And for this, we need to use, well, Runge's theorem is probably more than 150 years old. And I think he proved it more or less the same time when Weierstrass proved his approximation theorem for continuous functions in an interval. So it's really. But another ingredient is what to do with exhaustion. This is relatively recent, maybe 30 years old, theorem of Alexander Kekris from Caltech, which says that there exists a uniformly discrete, I will explain what does it mean, Borel cross-section I have to start. Well, I have to start. I first need to tell you what is a standard Borel space. Since this is a conference on complex analysis, and 3 years ago I didn't know what is a standard Borel space, I feel that I have to explain this. So standard Borel space, you start with Polish topological space. This is a topological space which is metrizable and which is, after introducing a metric, it is complete and separable. And then you introduce a Borel structure. On subsets of this, on subsets of this space. So this is a standard barrel space. So more or less it is unique when you fix when you fix its size, we deal with uncountable barrel standard barrel spaces. So in our situation, all of them are equivalent. So if you have standard barrel space, then and we have a reaction So this I had to tell you before I started to formulate Kekri's theory. So suppose that we have a standard barrel space. In our situation, also this is a standard barrel space, non-periodic entire functions are standard barrel space, all the spaces are standard barrel spaces, but we are interested in configurations, so apply this to configurations. So what Kekri's theorem says, that if you have a standard barrel space and free action of the complex plane by translation, then there exists a uniformly discrete barrel section of this set. What does it mean? This means that let me denote it by C. C is barrel, and intersection of C with each orbit of our action is a non-trivial, non-empty uniformly discrete set means that it is discrete, but also differences between points of the set cannot be a bigger or equal to some numerical constant. This constant is different on each one. This is very non-trivial theory. And using this, you can build even this cross-section with additional properties, but using this theorem, you can construct this barrel exhaustions, which will be which corresponds well with translations, which we can use instead of classical exhaustion in combination with Runge's theory. So this is how our proof works. But main difficulty lies here, and also one needs to modify a little bit classical Runge's theorem to make sure that on each step you do not spoil measurability. But well, for people who know several, Runge's theorem has plenty of proofs, and if you care, you can do these maps even piecewise continuous. So certainly, what Runge's theorem gives us. So certainly, this will not spoil measurability. Now, this is nice, and it is interesting.
Excuse me, so could you explain some idea about the proof of this Kekris? How to pronounce it? Kekris.
Kekris, right?
So could you explain some idea of this Kekris?
No, on staying on 1 foot, no. No, I can try maybe in a break, but not right now. Because it would leave me too far. Yeah, but this is a deep theorem. Here it's not important that this is complex plane. It works for action of RD. It works for action of any locally compact abelian group. Sometimes, probably in some version, even for amenable group, it will be, but not in general case. So what are other situations where What are other situations where there are, I know, two more very close situation where the same set of ideas will work. Where one situation is about solutions. So where it works, maybe I go back first. Works well. Solutions with the Poisson equation. One can do this with more general elliptic equation, but they told us that there will be some fire.
11:30.
11:30, it's not. Laplace G mu RT. So here mu is locally finite signed measures, so probably it's called radon signed measures, locally finite signed measure. Again, RD acts by translations on mu and on solutions to these equations. And you can ask absolutely the same question. For people to get used to subharmonic functions, this is really subharmonic version of Weierstrass theorem. It's called, how it's called? Weierstrass theorem in some books. Yeah, so if mu is non-negative, then it will be subharmonic function. If mu is 0, it will be harmonic. Right. So you can ask the same question, whether there exists right Borel inverse. So for each function, Laplacian gives us a measure, and the question is whether these functions are delta subharmonic, or you can work in C infinity category, what is written on the right-hand side. It's such kind of test. So Laplacian gives us a measure, and we want to know this map is continuous in weak topologies, and we want to know whether there exists right inverse, and again, everything is free, and right measurable inverse can exist. There is another situation. It is D-bar equation. Again, this works. H is P infinity. Again, this works well. We have Runge's theorem. We can apply Kekri's theorem. We can construct sections, and we're done. When it doesn't work, what are the simplest cases when one of these two components breaks down? One case is if we deal with unit disk instead of the complex plane. Now the group of automorphisms, it's non-amenable, and there is no analog of Kekri's theorem. Another situation is with Cn instead of C. In this situation, Runge's action is nice, sections exist, you can do exhaustions, but at least as far as Sasha Rashkovsky explained me, if I understand correctly, there is no hope for Runge's theorem, which will work in this situation. These are somehow limitations of what we did. And now
In these two cases, you don't know whether the
No.
conclusion is true.
No. Even I don't know the answer to simpler questions, which I will start right now. Discuss. There are many more other interesting questions here, but for my point, it's too. So I promise to put it into right context. And I need to start with this paper of Weiss. I think it was published in 98, but people say he mentions that he did it much earlier. So he introduced a concept of Lebesgue entire function. What it is, so you have a now it will be standard Lebesgue measure space. We will not write sigma algebra. And we have a pre-action of complex plane on this Lebesgue measure space. So measure is invariant, translation, measure is invariant. With respect to this measurable action. Here we are in Lebesgue category. So Lebesgue standard Lebesgue space, you can think simply that this is interval 0, 1 with classical Lebesgue measure. All other spaces are classification are. Then he gives a definition. So he says that a map F from X to C is Lebesgue. He says measurable, but because we speak about measurability in two different senses, I've changed measurable to Lebesgue. Lebesgue entire function. It's measurable. For new almost every point X. X. The function is new. I denote the action by TZ as before. Action. So on almost every orbit, you see an entire function. This is the definition. And his main theorem, this was the main result of this 7 pages paper, was that for any free action T, and for any X, for any choice of probability measure, measurable of Lebesgue entire function, this immediately gives you a lot of, so this shows that space of entire functions with action by translation is a kind of universal model. You can realize any action of complex plane by translations on a space of with some, there exists a probability measured on entire functions, which is stationary. The very existence of this measure was an old question asked to Mikhail, which is a simple consequence of this. But you can realize any action in the space of entire function. So this shows that this object really was neglected without reason. And what we are doing a Borel analog of this theorem. So I will not write it, but you can now easily modify this definition to define Borel entire function. So you need to start with Borel space. You say that function is Borel. You don't need to go to write almost everywhere. Just you need to know that this is entire function. And again, Borel entire functions are universal models. They always exist. For any measurable action, Borel measurable action, free Borel measurable action of complex plane, you can realize it on entire functions. And our main result can be formulated as a stronger version of existence of Borel entire functions. What we say that not only Borel entire functions exist, but for any discrete section, we can realize it having this discrete section as a divisor. That's all what I wanted to say, except of one thing. This is to Alex. I will write something in Ukrainian, but I will translate. Here I give a fusion of Ukrainian saying of Hebrew. So I wrote нехай щастить до 120, so Ukrainian saying is good, нехай щастить. Good luck, it's approximate. Sergey, how you would translate it? Good luck, and Hebrew saying is still 120. So here I combine those. Thank you very much.